All right, so as this says clearly, today is Monday. There are 3 lectures, so we'll go through in 3 parts. I've prepared extraordinary number of slides, like 300 slides. There's no way we can go through that. Yeah. I have no idea what any of you know. I know what all of my students know, and I do not know why they're here. But I do not know what any of you know here. So I'll go through this, and if you have, if you think that you haven't seen this before, or you want me to go slowly or go fast or things like that, let me know, and then I can adjust the pace. All the materials available to you, so you can always go through them. You can send me emails. At some point, I will respond to you. I will work that way. But in these 3 lectures, I only want to talk about how I think of combustion physics. And people think about it in different ways. When you do research, you will have your own access to combustion physics. You will do experiments. You can develop theory, or you can write codes, right? You can write computational codes. And I learned things by writing codes. Like the equations do not make sense to me directly. So when I write the codes, I realize, okay, this is what the equations mean. So when I talk about all of this, that's the viewpoint from which I come. So you'll see even in the slides that I make, this is how I've introduced how we're going to talk about computational physics, right? Or combustion physics. So there are 3 parts to this lecture series for the 3 days. Today we will look at the basics of computational modeling, like why are we doing this, what is the purpose, things like that, which sometimes is not very clear. And then we will look at large eddy simulation, which is, I think for the last 20 years, it's one of the most dominant themes in combustion research. So we'll look at the basics of large eddy simulation. What does it mean? Like, why do we need to do this, so on. And tomorrow, we will look at modeling for large eddy simulation and the outcomes from this. What are the limitations? What else we need to know, and so on. And on Wednesday, completely different topic on high-speed propulsion. This is very exciting to me. Like, I've worked on this for almost 20 years now. Scramjets, detonation engines, shocks, reactions. These are all fascinating topics to me. So I'll try to tell you what I know about this. Right? So 3 different lectures, 3 different motivations. Now, what I'll do is I have this iPad here. So if I need to write something, I'll have to switch over and then write it with that. I don't think it's going to work as cleanly as I say it's going to work. So I'll try to minimize writing anything here. I saw before that the previous professor had written things on the board, so I'll try to do something like this. Although it's too dark for you to see if I write there, I think. And my handwriting is not as good as Professor Matlon, so he's not going to figure it out. So this might be a better option. So we'll see. We'll see how it goes. All right, so turbulence, flame interaction, and large eddy simulation. So turbulence is what we need to first understand and master. We need to know what turbulence is about, right? And this is a vast field. There's a whole community of people who work only on turbulence, no reactions, just turbulence. And that's vastly bigger than all of us here. So you can think of the combustion world as maybe 4,000, 5,000 people. This is the total number of researchers. If you go to turbulence, that'll be 3 to 4 times that number. So this is a huge world out there. So we first have to know what is turbulence, why we care about it for our problems. How do we use it for any kind of physical device that we want to look at? And what are the challenges? What are the multidimensional challenges that it imposes? Too many things to click on. OK. So these are the background resources. And I've known all of them personally. And it's been very good talking to them. When you see people write books, and you go talk to them why they wrote those things, you get a different perspective than what you read in those books. So I really value reading Turbulent Combustion. It's a really good book to understand what is the role of turbulence in combustion, how do you model it, and so on, by Norbert Peters. To really understand turbulent flows, Steve Pope's book remains what I use for my classes. And of course, Combustion Physics by Ed Law from Princeton is what all the combustion, or the beginning combustion courses at the graduate level are all taught from across the country. Now, apart from this, in each slide, there will be some references to other papers, many of them my own. It's not, it's not some ego to put my own things. It's just easy to find it because it's all on my computer. I can easily take the stuff. You'll find similar work by many others, right? So it's not something so unique that only I can put those images. Okay, so we'll start with this. And I find this set of plots very interesting. So I was asked to give a lecture at the Combustion Symposium many years ago in Dublin. I think it was 2016 or 2018 or something like this. And I tried to see what has happened to simulations over this time. And many of you may not have been born in the 90s, and you might see stuff in the 2010s. And things have not changed from the 2010s to the 2020s. So I would say right now, they're very similar to this. And you can see this. If you just go through from left to right, you automatically see what's going on here. So initially, all the simulations we would do would look like this. They're simple flows. We had really pointed questions about what to understand from them. And we'll target the simulations only for that particular question. So the top picture there is a very famous paper from Jaberi and Payman Gibi. And it looks at how, in a compressible mixing layer, reactions can happen. It's a very specific problem that, of course, is useful in augmenters for aircrafts, for scramjet engines, even for gas turbines. But they took that problem, abstracted it out, and looked at the canonical exercise problem. Because at that time, we did not have enough insight into the physics. We did not have complex laser diagnostics. We could measure very simple things at that point. So simulations like that were very useful. But as you go further out, you can see that those simulations approach practical devices quite rapidly. So by the 2000s, in fact, this picture here in the middle that says Apte and Moyne, that's a landmark simulation. That's the first time an entire gas turbine engine has been simulated using unsteady flow physics with droplets and all this stuff. And this was done for a Pratt & Whitney engine, Pratt & Whitney 2000. And that simulation guided how that design effort will go through for that company. So that was a big change there. But going there to the next decade, you can see that things are becoming more photorealistic. They're as close to reality as you can imagine. And if you were to make measurements, they will look roughly the same. Okay? So you won't be able to qualitatively distinguish between the simulations and the experiments. But quantitatively, there's a big difference. And that bridge we have not been able to cross in the 15 years since these images were made. So this is the fundamental issue. Now, when things are complex and progress is very slow, you don't just stick everybody in the same problem. We all, all of us in this room, we don't work on the same topics all the time. And because there are certain topics where we can make a lot of progress, and other topics become less important or less critical at that stage. So you really have to think about what is the purpose of computational modeling, okay? And everything I showed you in the last picture, the things that were talked about there, they come under the umbrella of science of combustion. You do not know how some basic physical process couples with heat release, and now that's going to affect any other process you want to study, like how the velocity changes or what happens to the flow profile, things like that. So the science of combustion is always handled using high fidelity calculations. So this is the terminology. It just means that you throw everything you have at the biggest supercomputer that you can find, and you hope that you're getting very close to reality, right? So that's high fidelity simulations. Doesn't mean that everything is completely captured, but you are very close to doing that. Which also means that you cannot really tackle physical problems, like application problems, very closely, because even the best supercomputers are not there yet. And we'll come to that later. Now, a second part, which became more popular in the mid-90s and since then, is that if you model some of the physics, if you have good models for some of the physics, maybe you don't need the biggest supercomputers. You can use smaller computers, clusters, even desktop machines. And you can design systems, design engines. You can design entire gas turbines or augmenters or whatever else your goal is, right? So that was the second part of it. So that's for the design of combustion systems. But the last part is the most critical now, right? Because everything is data, And I'll be remiss if I don't use the phrase artificial intelligence, right? So everything is AI and ML. And to do that, there has to be a need. You don't just do AI and ML because someone else says it's important. There has to be a purpose for it. And our purpose, when we do combustion physics, comes from the economic need, right? So if you look at most engine manufacturers, a big portion of the revenue that they derive, the money that they derive, profits, come from maintenance of engines, not from selling the engines, but by maintaining them. And so you need some way to have this fleet of engines, maybe 100,000, maybe a million, who knows, like a big fleet of engines, and be able to predict for each one of them, when do you need to bring in from maintenance? I mean, if you all have cars, you know this. There's an engine light that goes up, and then you immediately go to the mechanic, and the guy charges $50,000 for nothing, right? So you know this. And that's the money that you want to make, yeah? So to do that, you have to be able to do these simulations, not using supercomputers. That's too expensive, but really fast. In fact, it should be so fast, it should be done on the engine itself, right? You should have computers on the engine itself, or at best, you collect the data and you do it in a data center that tells you how to bring in machines for repair, essentially. To me, these are the focal points. When we think of combustion modeling, we should think of this. And you have to choose a path. What is it that your research takes you? Is it towards the science of combustion or design of systems or these kind of operational details? And this last part did not exist for a long time. I mean, this was not, like when I was doing a PhD, this was the only thing. There was no design of combustion. You do this, and then someone who is the architect of the engine will look at your images and go, yeah, that's how I tune this side of it. It's all heuristic. But now we have this additional feature, right? So when we think of all of this modeling, we should take that into context. And this comes with its own set of constraints and the needs, right? So science of combustion, you do those simulations because you do not know enough about those systems. So it means that you cannot measure them very well, or you cannot do very detailed experiments. This could be things that are happening at very small scales, very large systems where you don't have access, optical access, things like that. Or the pressures are so high or the temperatures are so high you cannot send in laser beams and reliably get measurements. So those I call data-poor problems. So you have no access to data. You need to have some kind of intuition, a hypothesis, and you should test it out using the best methods that's available to you. And so which are generally high-fidelity calculations. So here, generating the data is very expensive. So unless your data is of use, the system you're building can recoup that cost, there's no reason to do high-fidelity simulations. So if you're building an object that sells for $2, you will not do high-fidelity calculations on a supercomputer, right? So it has to be exercised on machines that are inherently expensive, like an aircraft engine or a scramjet engine, right? So these are multi-million-dollar devices, and so there's a justification for doing these huge calculations. There are others which I call data-sufficient problems. So here, our physics is reasonably understood. We are qualitatively accurate, but not quantitatively. And we can do a lot of experiments. We're able to do many experiments. We can collect data reasonably well. They're still expensive, but not inaccessible. And there, because we have these experiments, we have this data, we know how to model them better. And so those simulations tend to be more predictive. And there are tools now that can make it more predictive, like uncertainty quantification, things like that. So these I call data-sufficient problems. So you have the capacity to generate them if the need arises, but perhaps that's not necessary and you won't go down a particular path. And then you have data-rich problems, like operation maintenance. A more pointy-headed way to say it is digital twins. So if you say the phrase digital twins, people will bow to you. But what you're essentially doing is taking data and trying to interpret some kind of pattern within it without knowing the true, or without thinking about the true physics. You don't care about the true physics. So those are the data-rich problems, and the generating data is inexpensive because you've already built the system. Like you might have a fleet of aircraft engines, so after that point, operation automatically generates the data You don't have to put extra cost towards it. Okay? And each one of these requires many different tools. And one thing that has changed in the last 30 years or so, 30 years ago, these simulations, you will take Navier-Stokes equations and you will beat it until the point you get some valuable information from this. But now that's not the case. You have access to multiple tools to sort of solve these problems. So on the top is the hierarchy of models that you can do for an internal combustion engine, going all the way from something that's very expensive, so the y-axis is the CPU cost, computational cost, and the x-axis tells you how many seconds you can simulate, right? So we'll come back to this notion again. But you have a whole set of models from really complex models to just empirical relations, maybe one-dimensional models and so on. And we also have methods to combine them, what is called multi-fidelity modeling hierarchy. So these are mathematical tools that have come from other fields, many different fields, and so we can utilize them. So you don't need to rely only on large eddy simulation or only on experiments to do something. We know how to effectively combine them. Yeah, so that's the additional benefit that we have. Now, what you cannot escape, and this is how we want to think about this problem, is that computers have changed. And computers have changed in a very specific way. Yeah? And here there's no getting around the fact that all the computers that we have today are driven by Silicon Valley for whatever purposes they have. If it's iPhones, there's a particular purpose. If it's AI, there's a particular purpose. And they generate all the hardware for everybody else, right? So even though we care a lot about combustion, we are a very small market. All of high-performance computing using supercomputers is still a tiny market. So as a result, nobody makes machines for us, computing machines for us. So we have to use whatever machines others have built for other purposes to the best possible way we can. Yeah. So computers have changed. And one of the things that has changed is this new idea of graphical processing units. So these are GPUs. And so if you use PyTorch or anything like this, they're all geared towards being used on GPUs, not on CPUs. And because you're using them on GPUs, there's a particular benefit to it. They're all very fast. You can process massive amounts of data. Or in our world, you can run very large grids for CFD purposes. So you can do trillions of grid points in your domain and be able to solve it. But it comes with certain restrictions. So what we can do in all of this is that you can simulate 100 square kilometers for 1 nanosecond. So that's possible now. 30 years ago, we could only simulate 1 square meter for 1 nanosecond. So we really increased the size we can simulate. But what we cannot do is simulate 1 square meter for 10 hours. So time remains inaccessible. So every problem that we have now, we have to recast it in a way that it's a short time, but very complex calculation. And you'll see this in how models are being developed. So they will have more complex math, more complex algorithms. So at every time step, you do a lot of calculations, but you're never going too far in time. And when those problems involve going a lot in time, then there's an issue. As a good example, if you have an aircraft engine and you change operating conditions, at some point you can blow out the flame. It's called the lean blowout limit. You have to characterize this before you can sell an engine. So you cannot, FAA won't authorize it if you don't say what the blowout limit for an engine is. Now, to do this in a simulation, you'll have to follow the same procedure they do in the experiments. You have to take it to some altitude. You have to make it show that it's burning correctly, and then slowly decrease the fuel flow rate. And at some point, the flame will blow out. But you do this over 30, 40 seconds, or even longer than that, a few minutes. Okay? The longest gas turbine simulation that I've seen is for about 10 to 20 milliseconds. So this is the best we can do. Okay? So lean blowout is just inaccessible even with the biggest computers you have now. So things like this, right? So these numbers, of course, they change every year. If your computers are built differently. If you have certain kinds of process, maybe you can go to longer times. But you cannot reach these really long times. So the most common thing, and we'll look at it on Wednesday, are detonation engines. In detonation engines, you really want to simulate 10 to 20 minutes of operation. So that's when you can really study what's going on. And right now, it's nowhere close to that. We can maybe simulate 3.5 to 4 milliseconds. And that's a big calculation. It's like 2 years ago, if you were to simulate 4 milliseconds, you will get a PhD thesis for it. Yeah, so this is not a simple task. So you have to remember this. So it's not none of this is all as it seems. Like just because computers are faster doesn't mean much. But the common perception is that everybody buys supercomputers. Like Elon Musk has a supercomputer, and Zuckerberg has a supercomputer. But it doesn't mean anything for our purposes, right? So we have to remember that. So there's a good way to think about it. And it came, this is not my original idea of thinking about it. So there's a guy, we have a lab, Los Alamos National Lab, which is the keeper of all our nuclear stuff. And they really care about doing large-scale computation. This is very important to them. And they always talk about it in a funny way. They want to fit a simulation on a supercomputer. They always want to fit a simulation on a supercomputer. And their simulations won't fit. They are complicated in a particular way that it won't fit on any machine that they can build. They cannot capture the time or the length scales and so on. So if you really think about it, any simulation that you do has two axes. The length scales that you want to capture, and we'll come to this later, it could be the geometry of the system. You might have a tiny injector and a 1 meter long geometry. So that gives you the range of length scales you have. Typical scramjet injectors could be like 0.5 millimeter diameter. The scramjet itself will be like 1.5 meters. So you have 0.5 millimeter to 1.5 meters. That's a range you can think about, right? So that's a range of length scales. There's also a range of time scales, which, if you do simple dimensional analysis, if you multiply it by some velocity, they should all work out. But it doesn't work like this, right? So there are specific physical processes that control the range of time scales, chemistry being one of them. If you have really fast chemistry, you can have time scales that are nanoseconds nature. And you can have devices that need to be operated, like I said, for detonation engines for 20 minutes or 30 minutes or so on. So that's a range of time scales that you have to capture. So that box is the capacity of the supercomputer you need. That area under the box is the capacity of the supercomputer that you need to be able to capture all of these time scales and all of these length scales. This machine does not exist, and it will not exist for the foreseeable future. Okay? So instead, we do certain things. So high fidelity simulations, or this, to me, it looks like a purple box. I do it as pink, but it looks purple. It's what can be fit without modeling. That's high fidelity simulations, or DNS. Yeah. And what it does is you can cover a range of length scales, not all of them, but a range. But because your computers can only do so many cycles a second, I don't know if you guys look at this at all, there are frequencies for CPU chips. And in the 90s, there was the Pentium processor. I feel very old saying this, but in the Pentium processor, and then there was at 500 megahertz or something like this. And it kept growing, and by 2010, it was at 2.5 gigahertz or something like that, right? So it was 1,000 times faster clock speed. But then it stopped. So now it's not at 400, gigahertz. It's not like that. It's still at 1.5 or 2 gigahertz, whatever it might be. The reason being that we decided if you keep increasing the clock speed, the power consumption goes up through the roof. And so we need different ways to build hardware. And so the clock speed is still roughly the same. It has not progressed. That means the amount of time you can capture using explicit time stepping for an ODE solver is restricted by your clock speed. And so the range of time scales goes down. So if you had a DNS, the DNS box, that area is the biggest supercomputer you have right now. So that's how you should think about it. That's the capacity. Or you can do reduced order modeling, like LES, or you can do any kind of data-driven modeling, whatever it might be. And what they do is they reduce the range of length scales that you capture directly using a grid, but instead allow you to access much longer time scales. Right? So that's a compromise that you make. So the area of the green box is the same as the area of the purple box if you want to use the whole computer. there are other methods, and I'll talk about this on Wednesday, which is called adaptive mesh refinement, which sort of uses this staggered pattern, and it allows you to, in some places use very high resolution longer times, other places lower resolution or lower time. So you can mix and match. Nothing is perfect. So when I say like this, it looks like AMR is a solution to the problem. It's not. It's just one way out of this hurdle. That's about it. It takes you some distance, but then it stops there. So you have to think about these things when you build models, right? So you have to keep this in mind. So this is my introduction to this. So I have a whole set of slides on turbulence after this. We are at 2:27, so it's 27 minutes into the lecture. Do you guys have any questions at all for me at this point? It's more fun for me if you guys ask questions. Otherwise, it's very boring. I can only read your faces for so long, then I just zone out at some point. So let's say you have Euler explicit scheme, okay? So x at n plus 1 is x at n plus some source terms times delta t, yeah? So that's typically something like this. Which means that you have to find x of n plus 1, and so the computer has to do this math, put it in a new register, that's your x of n plus 1. The time it takes to do that is determined by your clock cycle speed, okay? So if you want to do 100 billion steps, you need 100 billion clock cycles. And if that's not getting faster, you're limited. So that's the issue. It depends on what lens scales that you want to choose, right? So your laptop right now, I will say, is like an iPhone, I think is about 10 or so teraflops, I would say something like this, so that's the speed. The biggest supercomputers are 10 exaflops, right? So that's there is teraflops, then there's petaflops, and then there's exaflops. So 10 power 18 is exa. So we are, these laptops may be somewhere in between a petaflop and a teraflop, but more closer to the teraflop, so maybe like hundreds of teraflops. But it depends. You can buy, like if you want to mine Bitcoin, those chips are very fast. Yeah. Don't do that, but I'm just saying those chips are
What's the reason behind saying that you want 20 minutes of simulated runtime for IDEs to understand it?
It just, it's an estimation. So in the RDE, the critical problem right now is heat transfer to the walls, let's say. And to get a thermal steady state, it will take something like that. There are also other problems that are more specific that I can talk to you after, but that will also introduce long time scales, but something of that nature. Typically, if you want to do any steady state gas phase RDE, I think doing at least a second is necessary. And we are nowhere close to that. We are 2 orders of magnitude below that. So 20 minutes is very aspirational. Anything else? Okay. All right. So, turbulence. I've taught turbulence for a while. This is the first course I taught when I became a faculty member. I like teaching turbulence, and from last year, I'm not allowed to teach turbulence anymore because there are other faculty members who need to teach it. It's a very fascinating topic. There are many angles to it, and you can take it very far with any one angle. So what we'll do is we'll do it in 2 parts. Today I'm going to talk about turbulence in a very particular way. This is a classical way of looking at turbulence. And this is what we'll talk about. But you guys need to know these terms. Many of you might know this already. Knowing these terms is useful. And tomorrow, we'll change the perspective. So what I'm going to look at today and how Kolmogorov and the original thought leaders in turbulence approached it was using statistical theory. That's how they approached it. An alternative viewpoint, especially if you're doing data sciences, is to think of it as a dynamical system. So that we will look at tomorrow to think about it. For today, it's statistical closures. Yeah, that's what we'll look at. So why do we care about turbulence? It's excruciatingly unavoidable. There's no other way to put it. If I could avoid turbulence, I would at every given stage, but I cannot. There's no way to do that. And it shows up even if you make like the tiniest of mistakes, it will show up. And the moment it shows up, your world just goes crazy, right? Until turbulence is not there, there are only laminar flames and then chemistry, and then we know how to deal with them, and we are very good at that. And all these computers, no problem with computers. We can use a desktop machine, and then we are good. Everything is fine. The problem is it takes very little to make something turbulent. And the moment it becomes turbulent, then it goes haywire. So I think the saying, why is turbulence important, does not give due credit to turbulence. It's not that we chose to introduce turbulence. It will always be there. And we just have to deal with it somehow. Okay? And turbulence is not a feature that is, you can think of it as you want it, but it's not really. If there are other ways to do it, you would avoid it. Turbulence, to me, is a loss mechanism inside any combustor. It invariably takes bulk flow velocity, bulk kinetic energy, transfers it into this turbulent kinetic energy, and then dissipates it as heat. And anything that goes out as heat, you cannot use as a useful work. You cannot derive useful work from it. So by taking turbulent kinetic energy and then putting it into heat, you're losing some efficiency of the system. Now, I do exaggerate, of course, right? It's not, if you take any gas turbine combustor, yes, there is turbulence in this, but the turbulent kinetic energy is a very small portion of the bulk kinetic energy. It's not that high. And even the bulk kinetic energy is even a smaller portion of the total heat release that you're going to see inside the combustor, okay? So these are all, in varying proportions, not a big number. But even though it's a small number, it has very important effect on how we treat combustion, how we think about combustion. So the idea should always be that you think of turbulence as ephemeral. It's there for a short time. You don't use it, it'll go away. And if it goes away, then there's no way to get any useful work out of it. So you've lost everything, right? So whenever you design a system, you should think, I'm going to introduce turbulence knowingly, and I have a very short time span. In fact, that time span is measurable. It's called the integral time scale. And I have only this much time scale to deal with it, and afterwards it's going to do something else. So that's how I think of this. Now, there are various ways to look at this. I like this picture. I've shown this for 20 years now also. So that's the coast of Florida, if you guys are familiar with the US map on the top right. And it's every year, but this is one particular year when there's a hurricane off the coast of Florida. And I forget, every time I ask this number, I always forget this number. Do you guys know what's the length of the coast of Florida? Ruben, what's the length of the coast? He is from Florida. I don't think so, but let's say so. But it's still 200, let's say 200. I don't know. He should know, I don't know. It's 200 miles, let's say. So you can see that the hurricane spinning around, right? So you see that coherent structure that's moving around, and it's certainly much larger than the 200 miles. So it's a massive hurricane that's spinning around. Hopefully it doesn't hit the coast of Florida, but we will never know. It's been frozen for 20 years now. So and you see that arrow that I've drawn. So that's to indicate the diameter of the spinning vortex, right? And so that is an eddy. We call it an eddy. And it spins. It has certain kinetic energy associated with that spin. You can think of that to be somehow representative of the turbulence that's in the system. You can see this elsewhere. So this is actually flow behind a bluff body. If you look at the left, there's this green object. And there are many colors. I don't know what these colors are, but you can see that there are flow patterns and the same kind of rotating structures. You see it in that picture also. So that has a different length scale, a little bit smaller. It's always smaller than that bluff body. So there's a relation between them, right? So it's smaller than that. That one depends on so many other things. So it's much larger than, the Florida does not control the size of the hurricane. So it's much larger than this, right? There's one on Jupiter, I think, that's even much larger than this. I don't know how big it is. The red spot, is that what it's called? Yeah, so it's even bigger. And it's been raging for hundreds of years. So it's people claim it's becoming smaller, I don't know. So there's a length scale here, right? So we have to think differently now. So there's a length scale. So you can immediately assume you can foreshadow, or I'm foreshadowing a time scale that's going to show up in this picture, right? So we have to know length scale and time scale. So we always talk about turbulent motion, and it has the length, like the diameter there. And then it has some velocity associated with it. And then that gives you, if you divide, of course, a length by a velocity, you get a time, and that's your time scale, okay? So any eddy of size L has with it associated a time scale tau also, okay? So if I have a flow in which there are many, many different eddies of many, many different sizes, each will have its own characteristic velocity and its own characteristic time scale and a length scale. So these are instrumented properties for each one of those eddies. You can think of it that way. So the real question is, what happens to these eddies? So you have this initial eddy that is gigantic. We know that Florida hurricane did not last until now. Otherwise, we will know, right? It will be in the news. So it went away. At some point, it dissipated. It crossed over land or whatever, and it dissipated off, right? So these eddies are not static. They evolve in time, and they are going to do something. They're going to behave in a particular way, and that's what we want to understand. So you can think of these eddies in terms of these length scales, and I can characterize an initial Reynolds number RE0, which is based on the large length scale, the diameter of the hurricane, let's say, so something like that. So that's L0. Its corresponding velocity could be like U0. So U0, L0 divided by the kinematic viscosity, right? The physical viscosity divided by rho. So that's nu. So you do this, and then you get a Reynolds number. Now you see that it's a Reynolds number that depends on the length scale and the velocity. So which means that if I change the length scale and I change the velocity, the Reynolds number is going to change. So even within the same flow, for different eddies, I might have different Reynolds number. So we used to think of Reynolds number as something for a pipe. Like I say, what's the Reynolds number of this pipe? And then you look at the velocity of the inflow, the diameter of the pipe, the viscosity, and that's your Reynolds number. Here it's not like that. This Reynolds number itself is a time-varying, spatially varying quantity. So there are many different Reynolds numbers that you can define in a given turbulent flow, okay? So this is something to keep in mind. It's also a bit confusing. So there's a particular thing that happens. There's also a poem about it if you guys are interested. That large eddies have no option statistically but to break down into smaller eddies. So a big eddy of the size of the Florida coast cannot stay that way unless it's in the planet of Jupiter. It will always break down into smaller pieces, right? Of course, to make it clear, there can be forces that maintain that large eddy for a very long time, right? And then it will stay there for a long time. But within that process, it will still try to break down into smaller eddies. And that's a picture. I got it from this website. I found this picture much more useful than what I would draw with my hand, so I just took this one. So there are these initial eddies, and instead of thinking of eddies in two dimensions, like something that's circular, like spiral, this is actually like a sheet of paper that's been rolled. And so when you look at it from the top, it looks like a spiral, but when you look at it from the side, it's like a tall structure with the spiral thing on the top. And what happens is it pinches, that long structure pinches, breaks off, and forms this smaller eddies, okay? And if it keeps pinching off more and more and more, at some point, these eddies look what is called isotropic. And this is the biggest change or the biggest concept to learn from this. The notion that you can take any flow for the matter, the hurricane, gas turbine engine, internal combustion engine, scrambler, it doesn't matter. At some level, they all have the features of that system. So if you flow in a pipe, that flow is going to conform to the pipe. So the eddies initially are going to look like something like the pipe, right? But as it breaks down, these eddies lose that memory of what structure they come from, what flow they came from. And they all look the same. They all look isotropic. If you can imagine, this is not entirely correct what I'm saying, but you can imagine as a thought process, if you are able to zoom into a small section of any turbulent flow, if you go down to a particular scale and you look at the structure, the eddies there, you will not be able to say which flow that structure came from. They will all look the same. So that is the isotropic feature. Isotropic means that in every direction it looks the same. Okay? So it's isotropic in nature. So turbulence eddies break down and they become isotropic at some level. Now, because all flows, when the turbulence break down, it becomes isotropic. If you study only the isotropic part, you can come up with a universal theory, okay? Which is a concept we also need to understand in this era of AI and machine learning. The whole reason we're able to build models and use it in gas turbines or scramjets or internal combustion engines is because there's a principle of universality. You build a model in a particular system using some modeling hypothesis, you can transfer all of that to a different system. Transfer learning, right? Which is not feasible if you only use data. There has to be an intuitive construct to say, I can transfer this physics across these different applications. That's what this cascade theory tells you. You can take any large eddy, over time they will always break down, they'll become these small eddies. And you can take the energy of each one of these eddies, you can add them up based on their scale. So if you find eddies of 1 meter diameter, you take all their kinetic energy, you add it up. You take eddies of 0.5 meter diameter, you do the same. So if you add all of them up, now you have something like a histogram, okay? Because for each length scale, you can say how much energy eddies of that length scale will have. That's too simple, a histogram. So what people do in turbulence, they make it complicated. So you take that length scale, you take 1 over that length scale for no apparent reason, and you multiply by 2 pi, and you get frequency, okay? And that's the x-axis wave number in the top plot. So you take that histogram, you do some mathematical manipulation, you get that plot on the top. So the y-axis, now you have to remember, that's called the energy spectrum. The y and x-axis are both in log coordinates, so it's log of energy and it's log of wave number. If you plot it, you will always find this characteristic picture of initially the energy going up. So you have all these big eddies, they break down very quickly, and they form this intermediate scale, which is the integral length scale, and that's where the peak energy is. And then all those eddies keep breaking down, and when they become very small, if you think about the Reynolds number, right? For the large eddies, this number might be very large. As L becomes really, really small, that Reynolds number becomes very small. And when Reynolds number becomes very small, now viscosity becomes the dominant physics. So it just dissipates every one of those eddies, and no more eddies. It's just all uniform laminar flow inside one of those tiny pockets. And the dissipation is what transfers kinetic energy to heat. If it's a low Mach number flow, low speed flow, you don't notice any appreciable change in temperature. But if it's scramjet hypersonic flow, this is the game. You bring any flow to a rest, it's game over, right? There's so much temperature change, it'll melt down the device. So you have to remember this energy cascade process. Now, there are many aspects of this. These are not that critical, but it's good to know some of this at least. So there's this thing called dissipation rate, which is the rate at which you take turbulent kinetic energy and transfer and make it to heat, right? So the rate at which you're losing your ability to do useful work. And so that's the dissipation rate. And you have a scaling for this, which says that epsilon, if it's latex, that's VAR epsilon, right? That's that variable, is U naught cubed over L0. So you have the kinetic energy of the eddies, you divide it by L0, the length of the eddies, and you get this dissipation rate. Now, this is a funny object, epsilon. Epsilon says, the words say dissipation rate, and dissipation occurs because of viscosity, right? So you will always think dissipation rate should have viscosity in it. but it has no viscosity term in it, right? So dissipation itself is caused by viscosity, but the dissipation rate is independent of viscosity. It only depends on how much energy you're feeding into the large scales once you have the spectrum established. So that's what it says here. The dissipation rate is independent of viscosity. Also, although the cost of dissipation itself is this viscosity. So this is something to keep in mind. It's not so critical for what we're going to talk, but I think it's a useful construct to have. So now comes Kolmogorov, probably the most influential in all of turbulence. And Kolmogorov came up with these theories that, to this day, this is how we think about it. There are a lot of variations, modifications to it, but the primary hypotheses hold good. And the idea is that there are many different subparts to Kolmogorov's hypothesis, but these are important, so I'll have in these couple of slides the important ones. The hypothesis of local isotropy, and this is what we talked about before. If you take any anisotropic flow in a pipe, flow over a wing, whatever it might be, once you go to small enough scales, you lose that memory of what flow you came from. And it turns out that it doesn't have to be very small. When I think of very small, I'm thinking it's a 1 meter initial diameter. It has to go to like 1 nanometer. That to me is small. But it doesn't have to be that. It says that if it's 1 meter and you go to 1/6 of a meter, right, which is not that small, you already lose all the features of the big flow. This is the fundamental idea here. So there are some rules here, but ideally, you can define this length scale. There's a cryptic EI subscript for this. We'll come to this in a second. So LEI is the length at which you lose memory of the system you came from. And it turns out to be 1/6 of the integral length scale, which, if you think about it, is not that small. So once you have this, that's good to know, but you cannot do much with it, right? So you need some quantitative things, some tools you can have to say, okay, if I have to compare flows, what can I say about those flows? Reynolds number is a good way to compare different flows. You need some more features. And so he defines these additional quantities, and one of them is the Kolmogorov length scale. So the others, to me, are not that critical, but the Kolmogorov length scale is the bane of simulations. If you don't have Kolmogorov length scales, and if you don't have these features, doing the simulations will be a lot less expensive. Okay? So the Kolmogorov length scale, we talked about these eddies breaking down. At some point, they dissipate. How long can they stay as an eddy is determined by this Kolmogorov length scale. So on an average, eddies that are smaller than this eta will dissipate very fast, very quickly. So you don't have to really care about them. This is only on an average. There will always be eddies smaller than eta at any given time, but on an average, if you get to eta, you're going to dissipate out very quickly. So whenever you do simulations, modeling, whatever it might be, what you care about is what is eta for that particular flow. And when we talk about flames, we have to think what happens to this eta related to everything else, like, for instance, the laminar flame thickness, right? So things like that. So we have to identify relations between eta and some other physical construct from the flame itself. Okay? So eta is important to remember. Keep this in mind. And then there are scaling rules. Okay? So it tells you, if I change Reynolds number, how is eta going to change relative to the integral length scale that I have? And there are other rules. There are, for velocity and also for time, the Kolmogorov time scale, the rate at which the Kolmogorov eddies are turning around. Those are all to me, less important. The eta over L0 is the most critical thing. And it says here, eta over L0 scales as Reynolds number power minus 3/4. Now, 3/4 is very close to 1, right? 0.751. They're all roughly the same. So it tells you eta over L0 scales as 1 over Reynolds number, roughly, if you think, for estimation purposes. So if you take the same flow, you make the Reynolds number go up by a factor of 10, right? Eta is going to go down by a factor of 10. Yeah? So this is very important. As Reynolds number increases, your Kolmogorov length scale becomes smaller and smaller. Now, it's really -3/4, right? You cannot just cut corners and call it -1. But it's to give an estimation. Now, the thing that we don't really notice is that that eta is in one dimension. Turbulence is never one-dimensional. It's all three-dimensional. Okay? So the volume occupied by eta, which will be the cube of eta, eta cubed, right? Eddies of size eta will occupy eta cubed. That scales as Reynolds power -9/4, Reynolds power -2.5. And that is the single biggest problem. So if you think of CFD, when you do CFD, you have grid points in every direction, so you form cells, computational cells, finite volume. If you use finite volume methods, finite volume cells. That volume now has to be measured against this eta. And so if you have an eta that's very small, eta cubed that's very small, then your mesh size also has to become small. Otherwise, you cannot capture those flow physics. There's also additional aspect of time. So it doesn't scale as Reynolds power -9/4. If you think about CFD in practice, it will scale as Reynolds power -cubed. There's another factor that comes up. So every time you double the Reynolds number, your computational cost will go up by a factor of 8, which is a lot. Okay? So keep this in mind. There's only one additional thing you have to know, and then we'll move from turbulence, because this is not our course, and this is not what we want to focus on. I could teach turbulence for the entire semester, which is what I do, so this is not what you want to do all the time. There's only one other term that you have to know, which is what is called the inertial range. So you have the large eddies, and they're unstable, they're going to break down. Your viscosity is sitting at the other end. Think of like just eating all the eddies coming. This is insatiable. It just takes every eddy that of small size, eats it, and destroys it. So between these two extremes sit the middle part, whose only role is to transfer the eddies from the large to the mouth of viscosity. Right? So that's the part in the middle. And so that's the inertial range for turbulence. So you can write it this way. Again, this is again confusing. We went from 1/, length scale to length scale. Yeah, so it's not. So eta here is small, so it's on the left side. The axis is increasing, and you get a L0, which is the peak of that energy spectrum that we saw. Yeah? And you have this calligraphic L. This is essentially the size of your domain. So if it's the coast of Florida, according to Rubin, that's 200 miles. I do not know if that's correct. We should. You don't have access to the internet. It's like 300, let's say. It just grew by a factor of 50% already. I don't know, I should remember this. I ask this question every single time and I forget this. If it's a pipe, calligraphic L would be the diameter of the pipe, okay? I think I should teach estimation theory. Forget all of this. So 700 miles, L0 is going to be the most dominant eddies, which are always smaller than 700 miles. So it might be at 200 miles or 300 miles or something like this. And between that length scale and where dissipation takes over is the inertial subrange, where no energy is lost to viscosity. Mostly it's not lost to viscosity. The eddies keep breaking down and becoming smaller and smaller. Right? So that's the role for that. So if you put all of this together, you get this very characteristic plot, which if you do turbulent combustion, you have to know this. It's the energy spectrum in homogeneous isotropic turbulence. And what you see is this log plot for the x and y axis. Now, don't worry about the actual terminologies, because you see that it's not just energy, it's energy divided by some number and so on. They're all normalized so that different experiments can be compared together. And what you see is that, or a list of experiments across, from the 1960s all the way to 1994, And you see that they all collapse onto this curve. They give the exact same spectrum. So this is considered a proof that Kolmogorov hypothesis can be reliably used for our purposes. But what you need to know is the top right plot. There's a minus 5/3 slope in the inertial range, which is between the dominant L0 and the viscous dissipation range. So that minus 5/3 slope is very critical. This is how LES becomes viable for many applications. Okay? So you get a minus 5/3 slope. Now, I used to think this is some remarkable thing that you get minus 5/3 slope. And then there are all these papers, and my colleagues tell me that there are more papers elsewhere where you can take, do you guys know what this painting is? It's by Van Gogh, right? For his Starry Night. I was told it sits in the New York Metropolitan Museum of Art, of Modern Art, yeah. Okay, I was going to the wrong place, okay. So it sits there. So it's Van Gogh's Starry Night, yeah. So you can take this picture, cut out the cathedral and tree and all this stuff, take only the sky, pixelate it, right, red, green, and blue, and take Fourier transform. And if you do that, you will find the exact minus 5/3 spectrum for that also. This is another picture. Do you guys know what this is? I would be shocked if you guys knew what this is. No? I did not know either. It's called Chain Pier of Brighton by John Constable. So that picture, also you can remove all the low ground stuff, take the sky, and take Fourier transform. You'll get minus 5/3 spectrum. So now comes the dilemma, right? Are we seeing minus 5/3 spectrum everywhere because they exist, or as humans we can only see minus 5/3 spectrum? Right? We do not know. But this is there all the time. You do see the minus 5/3 spectrum in many different features that here. It's not always the case, though. If you have turbulence that's two-dimensional and not three-dimensional, you won't have the spectrum. So there's something about three-dimensionality that gives that particular slope. Anyways, something to know. Okay. So we're at 2:58. I can just go to turbulent combustion. I can take questions, or we can take a break. What seems reasonable? Yeah, few questions, a break, and then we come back. How about that, okay? Let's say 10 minutes. Is that reasonable? Yeah? Let's say 10 minutes, yeah. All right. Oh, this one? So, that's right. So think about it like a histogram, yeah? So if you take a PDF or a histogram, most of the density of the histogram would be where most of the samples are, right? So you can think of that peak to be where you find the most number of eddies. They also have, each of them have a lot of energy also. So if you add them up, then you get a lot of energy for those scales. So really large eddies are very unstable. So they break down rather quickly. And so this intermediate range is where you find the most number of eddies with the most energy. So you see an increase until then, because those are the dominant ones, and then again it decreases because they break down after that. There's no energy created. This is all at steady state. Yeah, there's not energy created. Yeah, that would be nuclear fusion. Yeah, it's not a. Any other questions? All right, good point to stop. So 10 minutes, 3:10, we come back, and then we'll look at turbulent combustion.